notes are about graphing polynomials. The first thing we're going to do is go through and talk about, in general, this is very general notes for this first part. In general, what do polynomials look like based on their degree? What possible shape could they have? So let's look at a constant function. How about just y equals 5, something like that. If you graph that, that's just going to be a horizontal line. How about a line, y equals 2x plus 1, something like that? I know that it might look something like this. Or maybe if I graphed y equals negative 3x, or something like that, it might slope downwards like this. So here's kind of a positive line. You could think of it in a negative line. Quadratic, hopefully we're experts in those. We know that maybe positive x squared, something like that, might look like that U shape, a parabola, and if we made it negative, it would open downwards. Now a cubic, maybe you've played around with these in the calculator, but a cubic might have this shape. It might sort of be kind of snake-like, have those two bumps, sort of a bump and then an upside down bump. If I graph a negative cubic, make that lead coefficient negative, it might look like that. You can find cubics that have larger bumps or smaller bumps, but in general this is kind of what a cubic could look like. A quartic, if you graph that, might have even more bumps, or maybe a negative quartic, something like that. Notice I kind of made both of those bumps the same height. One bump could be maybe a little bit higher than the other, we don't know, but in general something might look like that. A quintic could look like this, and we made it a negative quintic. There, I tried to make one where the bumps weren't exactly the same size. So you might notice some patterns. I'm going to stop at quintic. Of course, we could do 6th degree, 7th degree, etc., polynomials, but hopefully by now you've realized some sort of pattern. Notice on the linear function, the cubic function, and the quintic function, the arms are headed in different directions. If you look at sort of the left arm and the right arm, they're going in different directions. One's going up and one's going down in every case. If you look at the constant, the quadratic, and the quartic functions, both arms are always headed in the same direction, whether up or down. The difference is because of the degrees. We know that a linear, cubic, and quintic all have odd degrees there. Highest power is going to be odd, either 1, 3, or 5. I'm just going to put an O next to that so we can remember that that's an odd degree. And then the other ones have even degrees, just so we can really see the pattern here. So let's just summarize that. We know an even degree function has both arms in the same direction. Arms. Put that in quotes. I don't know if that's the technical term for the ends of the graph. In the same direction. And then an odd degree function, I guess we could say arms go in different directions. I won't say both. Arms in different directions. How do we know if they're up or down? Well, notice something about all of the positive graphs. So all of the graphs on the left side are positive. All have a lead coefficient that's positive, I guess I should say. All of the graphs on the right side have a lead coefficient that's negative. So there's something else you might notice. For the even degree functions, if they're positive, both arms go up. And of course we know if it's negative, then both arms must go down since they must go in the same direction. If it's an odd degree, notice which arm is always up. It's always that right arm in the odd degree function. So odd degree functions, if they're positive, meaning their lead coefficient is positive, only the right arm is up, and therefore the left arm must be going down, since in odd degree functions the arms go in different directions. So that's a quick summary of what the general shape will look like. Talking about where the arms are going, another way of describing that is by describing something called the end behavior of the graph, of the function. And that's a phrase that I'm going to use frequently, end behavior. That means what is the graph doing off at the ends? Don't really care about the bumps in the middle, how high they are, whatever. But describe the end behavior. That means tell me, is the right arm going up or down? Is the left arm going up or down? That's what end behavior means. And we'll talk more later about a nice mathematical way to concisely state the end behavior of a graph. Now let's get on to some actual graphing of these. Let's graph some actual specific ones and see how much we can figure out just from the form of the equation. We need to know something about the zeros and the multiplicities. I'll describe what that is in a minute before we can graph it. One thing we need to know, and we touched upon this in Chapter 5 as well, but this is the factor theorem. If x minus a is a factor, which means goes into evenly, of our function f of x, then x equals a is a zero of f of x. At the value of a, our function will be 0. In other words, f of a will be 0. That should make sense. Let's look at this function. Let's take f of x equals the quantity x minus 1 times x plus 2 times x minus 5. You can probably tell right away what 3 values make this function equal to 0. Because this function's in factored form, it's a lot easier to graph polynomials when they're in factored form. So we're going to do some examples sticking only in factored form for now. Let's see, we know the zeros are at 1, negative 2, and 5 because of that factor theorem. It should make sense. If you plug in 1, 1 minus 1 is 0, times, who cares, the whole function value will be 0. Let's see what else we know about this function. Can you find the degree? It's not in standard form, it's in factored form. Don't bother multiplying it out, we don't need to do that, but I bet you can imagine that if we did, the degree would be 3, so it is a cubic. Also, if you can imagine multiplying this out, we would get an x cubed as a first term, so it is a positive cubic. So that means the right arm is going up, the left arm is going down. Let's sketch what that might look like. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. There's negative 2, 1, and 5. Those are the 3 zeros. I can plot those first. I know the right arm must go up. I know it has to pass through all of these zeros. That's a pretty rough sketch of our function. Notice I didn't even fill in the y values. I don't even really care right now. Actually, I guess I could find the y-intercept by just plugging in 0. That would be pretty easy, but I don't really care. I just want to get the basic shape and the zeros for now. Let's look at something a little bit different. How about y equals the quantity x minus 1 squared times x plus 2? You'll notice it's still a cubic, it's still positive, but what the heck does this squared thing do to the 0? I mean, 1 0 is still a 0, but because that factor is squared, we would say that that 0 has a multiplicity of 2. A multiplicity is the number of times that that factor shows up in the equation. So squared means that it was really x minus 1 times x minus 1, which shows up twice. X plus 2, let's see, that tells us that another 0 is at negative 2, 0. And that we can just say it has a multiplicity of 1. We wouldn't even really say anything about multiplicity. What's going to happen at the multiplicity of 2? It turns out that the graph will bounce at any even multiplicity. So if the multiplicity was 6 or 4, the graph would kind of bounce off that 0. And that's because when you're squaring a number, whether it was positive or negative, when you square it, you turn it positive, which means if the original value of the function was positive, it's still positive. If it was negative, it's still negative. It's not changing the value of the function. So that means that on either side of the 0, it has the same positive or negative ness that it had on the other side of the 0. So you can play around with the numbers and hopefully convince yourself that if you're squaring a factor, the graph, in fact, kind of bounces there. So let's see what that would look like. There's 1, here's negative 2. I know that there are zeros at both of them. I know it's cubic, it's positive, so that right arm has to go up. The graph will bounce at our 0 of 1. What that looks like is it'll kind of touch it and then come right up. And then at negative 2, it just has to cross through, just like we saw before. So that's what I mean by bounce. I mean, it touches it and then just comes right back up off. It's kind of just sitting, that bump is kind of just sitting right on the x-axis. Let's just do one more example. How about g of x equals negative x times the quantity x minus 3 squared times the quantity x plus 2. First thing you might notice is that it's negative. There's a negative sign out front. Can you find the degree? If you multiply it out, you will actually get a degree 4, which is a quartic. So far we know that both arms are pointing down, and we know it has a 0 at 3, 0. That one's kind of easy to see. Negative 2, 0. These are the zeros. And don't forget about this x. Most common mistake is to forget about that x. That means that there's a 0 at 0, 0. The expression x is the same as the expression x minus 0. So that just means that if you plug in 0 for x, that whole function will go to 0. So it is telling us another 0. Don't forget about that one. The other thing we want to know is that the 0 of 3 had a multiplicity of 2. Therefore, the graph is going to bounce there. It's an even multiplicity. At the other zeros, it's just going to cross through. Let's see if we can put all that together and see what we get. Let's see, so our zeros were at 0, 0, negative 2, 0, and 3, 0. It was a negative quartic, so both arms are going to point down. I can even start with that if I want, just to kind of give myself a little skeleton there. I know that it had to bounce off the 3, 0, 1. That was this one. I guess I should label these. So bounce, and then it had to cross through and cross through. There we go. There's our negative quartic sketch. Notice these are not super accurate, but they're really good for just getting a general sense of the shape and where the zeros are. Good luck with the practice.